I'm delighted to invite Jerry Chow to the stage. Jerry is a world-renowned experimental physicist. He played an absolutely critical role in putting the first ever quantum computer available in the cloud for all kinds of exploration for students and research. And Jerry now leads our experimental quantum systems development on behalf of all of IBM Quantum. So Jerry Chow, please come to the stage.
Thank you. Okay, well, I'm really honored to be here at the second Hudson Forum to get the chance to really follow that amazing talk from Professor Debashi. That was amazing. I love to hear all about the mathematics. And I'm going to switch gears a little bit, right, and talk to you a little bit about quantum. And this building that you're all sitting in has really a renowned history in terms of, I think the words quantum information were first written by Charlie Bennett right here. And so what better place than here to have this discussion. And so we have a really exciting panel coming up, right? And some really esteemed speakers. But I want to steal a few minutes beforehand just to really give a backdrop about why we're so excited about quantum computing, right? Why we really see as truly a critical piece to push forward the future of all computing. Now, I think the first thing to remind you, right, is that even given all the computing resources we have today and what we know about traditional computers, there are problems that they just cannot solve, right? And there are problems that scale exponentially in the size of the variables, right, or the resources that they require. And our traditional computers aren't meant for that. But quantum computing really gives us a different tact at handling certain types of problems. It's really the only fundamental difference, a fundamental change in the format of how we do the underlying mathematics to perform computation in a different way. And it follows the laws of quantum mechanics. It allows us to really represent data using sort of the natural uncertainty of nature, right, in a different way. And this different representation opens up new avenues for us to explore problems in an entirely different way that can be more efficient for certain types of problems. GPUs and classical hardware are just not made for these types of problems. And so really, quantum computing is not just a faster, right, or better version of classical computing. We obviously know about the progression of Moore's law and how much has brought us to the point where we are today. But here, quantum is this absolutely new branch of computing. To get down to some of the basics, right, in terms of what we are actually computing, right, there's certainly how we represent information. It's different. It's not with bits. It's with qubits. These qubits follow the fundamental laws of quantum mechanics, right? So they take on certain properties such as superposition. They can be entangled with one another. We can perform quantum measurements, right? They can interfere with one another. In essence, the mathematics is what's different. And I've heard Scott Aronson, for example, say in the field that you can think of it really as you're performing matrix mathematics, but with negative signs. This allows you to do things like reversible computations and so forth, which really changes what you can look at and the types of problems that one can look at. So whereas the qubit is this fundamental unit of information by which we process, the computational construct that we actually want to use is called the quantum circuit. Right? So the quantum circuit is basically formed of a number of instructions that are performed across a number of qubits. And this advances your computation, right? Now, the complexity of the problem that you want to solve is based off of the complexity of this quantum circuit that you represent. This is it's pretty similar to how you actually would do a digital circuit with various operations performing across a number of bits. But the challenge for quantum computing is that we're limited today in terms of the size of these quantum circuits that we can actually perform. There's decoherence that arises in any sort of physical instantiation of qubits, which limits the depth or the number of operations that one can perform. But it's important to really understand that to measure the progress of where we're going with quantum computing, you need to know how many qubits in your quantum circuit you have, and also how deep, how many total operations are we able to perform. And this is leveraging techniques from handling errors and noise, which you're going to hear about from some of our esteemed colleagues on the panel in a little bit. But depending on the quantum circuit you have the opportunity to really look at some very, very challenging problems that are of real societal impact. Right? Looking at things that are like simulating nature. Of course, there's the well-known Shor's algorithm for factoring, right, which is impactful for breaking encryption. But also handling various types of mathematical problems with complex data, as well as looking at optimization and search. Now, we took a landscape of all the potential theoretical written down applications out there and plotted it in this graph that you see behind me of looking at what are some of the resource counts that you need in terms of the number of qubits and the number of gates to really achieve some of those applications that have been written down. And what you can see is you're in the thousands of qubits and potentially billions or tens of billions or even more of gates. Seems like a lot, right? Where we are, we've just entered that red dot region in terms of current existing hardware at about 100 qubits and several thousands of gates. That doesn't sound like much, but actually it's a very important milestone. We're in this period which we call utility. We're able to actually have systems and real quantum computing systems that can perform accurate calculations at that scale. And it's only the beginning where we are starting to push against what can potentially be compared with the best that can be done classically. Right? So this juncture of hitting this utility scale tells us that now we can actually trust that quantum computers can execute circuits accurately. Last year, we showed this in a Nature paper that was published, that even with these noisy systems using error mitigation techniques, that we can get accurate results on 127 qubits. And this is beyond what you can do with brute force classical computation. But it becomes a way for you to validate approximate classical computational methods. That's an important point, right? What it says is that a quantum computer can actually run quantum circuits better than you can potentially use a classical approximation of that. Now, this error utility is really just the beginning. We have a roadmap at IBM Quantum that goes out into the 2030s. I'm not going to go into all the details here because there's a lot of various elements in terms of the full stack that we're trying to build, from the hardware advancements in terms of the underlying quantum processors, up through the stack in terms of the software and applications experience for users to really achieve a frictionless experience with running their problems. But here, really on this timeline, we're putting our stake in the ground for how we are improving the underlying systems to achieve both the scale as well as that depth, the number of gates, right? Increasing that capability year after year through this roadmap. And in fact, we have a very important milestone near the end of the decade at 2029, where we want to demonstrate a fully fault-tolerant, error-corrected quantum computer, which can achieve tens of millions and hundreds of millions of gates across several hundreds of qubits. And that's going to be a really, really important milestone. Now, as we build this, right, there's an important piece that I want to talk about to end, really, is that how you actually will access quantum computing is not just on its own, right? It's not something that is going to just simply replace all of your classical computers today. But in fact, it is really part of a cohesive infrastructure that involves other computing resources that we have. And so there's this idea that we've coined quantum-centric supercomputing, right? And it is that we expect quantum processing units with GPUs and traditional CPUs to really all work together to unlock the future of computing, right? The point is, quantum isn't just consumable on its own. There's parts of it that with their various speeds and feeds that you need to take care of how the information is passed, where you perform parallel operations, parallel computational workflows, either in the classical domain or in the quantum domain. This is very akin to what we know and love with high-performance computing today, but we're just adding in this additional capability of running things on a quantum processing unit as well. And so this vision of quantum-centric supercomputing is what's going to really drive us forward for handling some of the most challenging problems. And in fact, we already have certain indicators that this is really an exciting direction to go. Earlier this year, we just published a paper with collaborators at RIKEN looking at the complex molecular structure of iron sulfide, leveraging this quantum-centric supercomputing architecture, combining results from Fugaku, right? 6,400 nodes of Fugaku, which is the high-performance computing node system out in Japan, with our IBM Quantum Heron processor, and really finding ways to push the envelope in terms of what can be simulated using this type of architecture. Now, you're all going to be in for a treat. Sign up for the tour. You're going to see our IBM Quantum System 2. This is the architecture that is modular and scalable that's going to allow us to build this type of quantum-centric supercomputing vision. And I'll just leave you with this one chart again, but to show you that with this type of landscape, we expect to really fill in that space, move into through this area of utility to find advantage and look for heuristic advantages using the quantum-centric supercomputing architecture to explore algorithm development and really to use the underlying hardware. And with that, thank you. And now I'd like to introduce the panel, where they will touch on a number of these topics and tell you more about how they are really helping to drive this entire field forward. So I'd like to welcome my colleague, Sarah Sheldon, IBM Senior Manager of Quantum Theory and Capabilities, Michael Biercuk, Travis Humble, and Sabrina Maniscalco.
Great. Thank you, Jerry, for that great introduction to quantum computing and where we are today. We have a great panel of quantum experts here today, so we're going to dive a little bit more deeply into some of the topics that Jerry introduced. And so I'm going to kick things off with a few questions, and we'll have some time for audience Q&A towards the end. So think about what you want to ask while we're talking. So I want to start kind of continuing on this theme of math is everywhere and talk about the importance of algorithms development for quantum computing. So Jerry mentioned, things are operating differently in the quantum world. We have these bits that are based on using quantum mechanics. So I want to open to the panel with, maybe we could say a little bit more about how quantum algorithms work differently and what's the importance of algorithms development in the near term. Maybe Sabrina will start with
Sure, of course. First of all, I have to say it's very exciting to be here, and I was very inspired by the previous talk, especially because I think that it is a special role if you consider mathematics and quantum physics. I think mathematics is the language we use to describe the universe, but it's peculiar because in quantum physics, we really can only use mathematics to describe correctly the behavior of quantum particles or to describe correctly how an algorithms work. If we don't use it, we use metaphors. So we say a quantum superposition means a qubit can be up and down, here or there, but it's just metaphors. And metaphors can be sometimes tricky. We need to use them. The truth is that mathematics describes algorithms, and mathematics is what we use to implement algorithms and run on quantum computers. And so in general, once we started to deploy and to use quantum computers that are at the level of what we described before, with hundreds of qubits, utility scale level, it became clear that the type of algorithms that need to develop for them to become useful to treat problems that are of importance for society are different, fundamentally different from what we can do classically, because the quantum logic is different, precisely because of these properties. And I will describe maybe later some of the way in which this can be applied to healthcare and life sciences. This is the topic of my startup, Algorithmic. And in particular, what comes eventually, as one of the fundamental difference is those phases that you were mentioning before that basically characterize the propagation of state vectors. So that describes quantum systems, and that describes also the logical state of the quantum computer as it evolves through gates. So these phases play a key role, and it's the fact that quantum mechanics works with amplitudes rather than the probabilities in the propagation. So this is just in general terms some observations, and it's fantastic to see how these mathematical properties and physical properties can nowadays be used to bring value to different industries and different sectors already now.
I might add on to this that you all can imagine understanding quantum mechanics itself is incredibly challenging. We often talk about how it's non-intuitive and difficult to accept some of the consequences of it. Now, taking that and translating it into a useful mathematics, an algorithm that can be applied on the state-of-the-art hardware that we were just hearing about, it's an enormous challenge. So I do think that the algorithms play an important part because it helps us conceptualize this idea of quantum physics, quantum mechanics, in a way that connects back to computation. So that intersection between physics and computing is a new playground when you add this quantum element to it. It's not immediately obvious how you would construct these algorithms or necessarily how you would make them efficient. I feel like I'm very good at making bad algorithms. Making good ones takes a little bit more work.
So can I take some light? I'll ask the audience's permission. Can I take the license to recognize that all of you are incredibly smart people and maybe in this audience want to hear less company line and more just interesting stuff? Is that okay? So I think, I feel like the first talk gave me full license to do that. My company, Q-Control, is focused on making the hardware perform better, and we build algorithms that do that, right? And a key part of operating a quantum computer is not just thinking about the so-called logical level. This is where, by analogy, we talk about like Booleans, the equivalent of ands and ors and whatnot. That's what Jerry was showing in the diagram of the quantum circuit, in a sense. There's also what's going down at the hardware level. We're actually manipulating nature on its most fundamental level. And we have to always build a connection between these two worlds that are very different, right? The world in which we live, which is the classical world, where you can sit on your chair and you don't fall through it. And then this other world, the quantum world, where the rules feel very different, right? Where we talk about probabilities and particles in two places at once. And we talk about all these things that are often described as spooky or counterintuitive. We have to bring them together. And the kinds of things that I've focused on in my career and in our company are about making those two things talk to each other in an efficient way so we really can build the kinds of applications that Sabrina or others have been focusing on. And so I wanted to spend just a second to talk about that, like two problems that we have. One problem is that quantum systems tend to break. They're very fragile. Why don't you fall through your chair? In a sense, because a lot of the weird quantum stuff breaks at big scales. Now, when we're trying to build machines that run applications, we have a lot of work to do to fix this. And the way we do this, again, to connect with the first talk, is to turn back time. What we actually do is we see these quantum systems changing over time. They evolve, and they kind of get off course. And then we have to turn back the clock to make them go backwards, to go back onto the straight line that we're trying to put them on. And the way we do this is using the mathematics of, sorry for those of you who this is not meaningful, but for Rademacher functions and Walsh functions, it's this kind of mathematical functional analysis that tells us how we change time and time evolution in quantum systems in order to keep it on the straight and narrow, to keep the quantum system living the way we want. The other part is how do we connect quantum things, which evolve continuously, again, going back to the first talk, to regular computers that don't evolve continuously. Regular computers, you all know they have like a 3 gigahertz clock. It's square wave, it goes up and down. And you only trigger an action on the edge of a clock. How do you connect these two things together? It's actually an extraordinarily challenging problem that again connects to this question of functional analysis. You can use these square waves, as I was just mentioning, to connect the time evolution and turning back time periodically all the way back to how you interface a quantum computer with a classical computer. And all of these are the kinds of fun mathematical and physics and control engineering challenges that we face, not just in designing logical algorithms, but in actually making them run on real hardware such that they give you the right answer.
Great, thank you. All right, a lot to dive into here. I want to pick up on this thread of the quantum world and the classical world working together. And Jerry mentioned this picture of quantum-centric supercomputing and this idea that we expect quantum computers to work together with classical computers. So maybe Travis, at Oak Ridge, you host some of the world's best HPC systems. How do you see the future kind of looking for bringing quantum into that HPC picture?
This is an incredibly hot topic at the moment. So Oak Ridge is the site of the Frontier supercomputer system, which is currently ranked #1 in the world on the top 500 list, is always evaluating what's the next big thing in supercomputing. And in fact, currently we're under consideration now for designing what would be a 10 to 1,000 increase in the computational power measured through flops, floating point operations per second. But that may not be the right measure when you start adding in new types of hardware like quantum computing, where the problems that you can solve may be very different from the problems we solve with our current approaches. That mixture of computational models opens us up to really a new frontier of problems that we may have avoided in the past precisely because there was an incompatibility with our classical way of thinking about things that goes away when we add quantum algorithmic methods in play. The other part that starts to make a connection here is in the energy consumption of these systems. One of the reasons we don't currently have a bigger supercomputer at Oak Ridge is we don't have enough power to support that. One, it's expensive, and two, just the infrastructure required. Quantum computing itself may offer some alternatives to energy-efficient computing. So both of those pieces together, I think, are an incredibly important part of this future paradigm of quantum and HPC coming together. But an absolutely critical piece will be devising the algorithms that can make the best of both worlds. This is what's been called hybrid computing or quantum classical computing. That, I think we're just starting to get into. The work that Jerry highlighted with Riken on how you could use a parallelized approach to decompose a problem, how you could then hand off tasks to these quantum kernels. I think that's an exciting endeavor to look towards, but it requires us to rethink the architecture of the system as well as how the algorithms map onto that architecture.
Great. Maybe I'll ask Sabrina if you want to add on to that, just this picture of developing algorithms where there's sort of a quantum subroutine, or maybe there's some bits of classical subroutines that you're combining together. Maybe you could talk about some of the things you're working on and how you see that picture.
Yes, of course. I also agree this is really one of the main future avenues. Some of the things we do, specifically in healthcare and life sciences, are such that it is important to use quantum computers for what they are really good at. So for example, I'll just make a concrete example. If we want to understand better or simulate the state of a given molecule, maybe the ground or the exciting state of a molecule, we want to use a quantum computer in order to create sufficient amount of entanglement of correlations that are this multi-reference character that in some cases is crucial really to simulate these systems. But in the end, we want to use, after we read out the quantum computer, we want to use tensor network methods in order to increase really the expressivity of the state, and therefore add parameters, millions of more parameters that would allow the combination of quantum computer, in this case with GPUs, because everything we do is tensor network-based method, to provide more than what individual quantum computers and GPU or tensor network methods can do. So the combination combination of both goes beyond what the two techniques independently can do. And this is, I think, the key to enable applications that are really so complex that we are struggling with any classical methods, including AI, including tensor network-based GPU methods. We do need seamless integration between these two technologies in order to tackle these categories of problems.
Yes, great. So maybe to get to why also we want to kind of bring quantum and classical together, especially in the near term, is we're trying to get the most out of the quantum computers that we have today. So we talk about noise in these systems, and Jerry mentioned getting to higher quality systems, being able to do longer depth circuits and get to harder problems. Maybe Mike, could you say a little bit about what we mean when we're talking about noise in quantum computers, and what are ways that we might deal with it in the near term or in the long term?
Sure. So I think the starting point is this realization that quantum computing is just different than conventional computing. And one of the ways in which it's different is that in conventional classical computing, we have the benefit that we encode information in this digital way, right? As long as a voltage on a transistor is above some level, you say it's always a 1. It doesn't matter if the voltage fluctuates. As long as it's above that level, it's always a 1. And as long as it's below, it's always a 0. That gives you huge resilience against little tiny changes. But quantum computing does not work like that. Quantum computing is, in some very specific ways, a little bit more analog, right? It has these continuous values that matter. We track the phase of the wave function. We track the amplitude in a continuous way. And as such, any little perturbations can lead it astray. And so our task is to try and address that. Now, there are broadly 3 ways we think about doing that. The first way is where I tend to focus, which is how do I manipulate the hardware in the best way to make it immune to these fluctuations? The hardware itself is sensitive, but I'm going to use these mathematical tricks in order to turn back time in just the right way, such that at the end of my computation, it looks like there was no noise, right? There was no error. The next way that I think Sabrina may talk more about is post-processing. You deal with the fact that it just kind of sucks and there's errors, and then you try and see through the noise. I think that was even the subtitle of the Nature paper, Seeing Through the Noise for IBM's work. Then the last way is to actually identify and fix the errors. That's something called quantum error correction. Now, many of you may have heard about this. It's in the news a lot from IBM, from other organizations. It's a huge scientific endeavor. It's very, very resource intensive. And so anytime you hear the words quantum error correction, you should broadly think, not today. You should think sometime in the future, this is just a way we can identify and fix the errors that get through. In the interim, while the machines are modestly sized, hundreds of these fundamental logic elements like we have today, we think that this combination of operate the hardware in the right way to make it less error prone, and then combine some smart post-processing like we just heard about, that is the best way to get the most value out of the machines we have. And of course, as we go in a continual fashion, we'll add new tricks, including quantum error correction. But this is the bane of our existence. Like, this is what we spend almost all of our time and research effort and dollars trying to address. Right? So it's, for companies like mine that specialize in this, we see this as potentially very lucrative, but it is a huge aspect of what drives the activity in the community.
Great, thank you. Sabrina, did you want to add on?
Yeah, maybe I could add, I totally agree. I could add, however, that these two paradigms of if you want, handling errors that are error suppression and mitigation and error correction, they are not separate words. We will not see at some point a sharp transition going from the computers we have today to fault-tolerant quantum computers. It will happen gradually, and the techniques will be merged because there will always be the need of using all of them in combination. Until we go to full fault tolerance. So it's not, we should not think in terms of different paradigms of computing. They are really something which smoothly will merge and be combined as the technology progresses.
So I'm sorry, can I pick up on that again? Has anybody in the room heard of, not the quantum people, has any of you heard of fault-tolerant quantum computing as a concept? Do you hear about this in the media sometimes? Have you ever heard of quantum error correction? Okay. So I want to say something controversial. We're among friends. As an experimentalist, I feel afflicted by theorists who have built this notion that you either, as Sabrina was saying, you either have a bad, useless quantum computer, or you have this perfect thing that works in the asymptotic limit of infinitely large numbers of qubits and infinitely low error rates. And they forget that we don't live at asymptotic limits, right? We live in a finite world. And so I just wanted to emphasize this point that everything that matters is in the finite limit, where we merge these things together and we make the systems good enough to do useful stuff, as opposed to only good enough to do infinitely large things.
Yeah, absolutely. I can add very quickly, I totally agree. I mean, there have been recently many so-called no-go theorems that are done really studying asymptotics limit. And these are really, in a way, in some sense, they can be dangerous because they can drive the opinion of the community towards directions which are actually not relevant. I like to always quote this way of saying, I don't remember who said it first, but in theory there is no difference between theory and practice, but in practice there is. And actually, yes, we need to do things on the quantum computers in order to figure out how to make them work, and we are progressing at an incredible speed, so it's happening.
Awesome. Yes, I think we're all in agreement that there's a lot we can do now and a lot more in development from the near term, and making this transition into that kind of future error-corrected picture. But now that we have these systems that are at this kind of threshold of being able to do things that we can't simulate classically, I think we're seeing a huge kind of boom in creativity on what we might do in the near term. Maybe, Travis, I'll go to you. I want to start talking about what we would want to use a quantum computer for. I know you're interested in using quantum computers for scientific discovery. What do you think the impact might be there?
Yeah, this is a really interesting question. If you think back to the chart that Jerry had put up, and then the point in your question, that we're getting to a stage where the quantum computer can solve problems that we cannot solve with conventional methods. How do you check that? How do you check that you solved it correctly? It's actually rather delicate to debug a quantum computer at that software algorithmic level. For me, when you start adding quantum computing as a tool into your workflow for scientific discovery, you're now setting things up for experimental validation. At Oak Ridge in particular, we're very interested in materials science. So synthesizing and characterizing new materials, we have some of the world's best instruments for this purpose. We use that fastest supercomputer specifically for modeling and simulation of what the outcomes from those measurements should be. We're reaching the point now where we want to use the quantum computer to simulate what would be the signal coming out of a neutron scattering source or an electron microscope, because those signals will ultimately tell us whether or not the quantum computer solved the problem correctly. Nature, this has come up a couple times now, still reigns supreme in defining what is the relative baseline for accuracy. So our quantum computers, regardless of methods and algorithms, must be held accountable to that standard. So at least from my perspective, the materials problem, the chemistry problem, high energy and low energy physics, all of these are great opportunities for us to take advantage of nature and the quantum world around us as a way to inform and validate the experimental progress.
Then maybe to move on to other areas of science where we might want to use a quantum computer. I know we have more talks later today on genetics and neuroscience. Sabrina, I wanted to ask you, what do you think we might use a quantum computer for in the areas of healthcare and life sciences?
Yes, this is exactly, I think, one of the most impactful applications of quantum computers. I can describe briefly three different types of use cases. we are working on at the moment. They are all end-user driven. It's really important in the field to identify problems that are of importance for end users and where we can find a match with what quantum computers can do today and in the near future, and also in the far future, of course. And one of the first problems is related, it's a collaboration with Cleveland Clinic, with Dr. Lara Jehai, who is an expert in epilepsy. And there we are using quantum walks. These are specific quantum algorithms to better understand the behavior of the networks that can be extracted from EEG time series. So in particular, the problem is to understand why for certain patients surgery helps and for others doesn't. And they've developed a number of techniques which use, for example, machine learning in order to analyze the networks of the EEG nodes before and after surgery for categorizing different patients. But quantum walks can be used in order to grasp correlations between the different parts of the brains. In a way, we do know that they are somehow successful in this, because we have been already studying quantum walks, for example, on protein-protein interaction networks and in the field of gene prioritization. This is a work done together with Professor Maniscalco from Harvard Medical School, and we are able to prove that they outperform classical methods like random walk methods. And this is because of the different ways in which quantum walks evolve. The diffusion process is dramatically different. We go back to phases once again. And then again, this is a way in which we can bring value now, because we can already extract, for example, new genes related to the disease that have biological meaning, really. And this is specifically use case that we considered are related to coronary artery disease, and so on and so forth. And then there is a second category of problems, which is where we are using, again, in collaboration with IBM and the Cleveland Clinic in a project funded by the Wellcome Leap Quantum for Bio. We are using quantum computers to understand the interaction between drugs and light, specifically photodynamic therapy for treating cancer. And there, what is important is that you really need to identify why quantum computers could be useful for this. And our colleagues at Cleveland Clinic told us that they really have really a hard time to model the interaction of drug with light, because you need to understand also what are the properties of the excited states, and excited states have multi-reference characters. This means they are highly entangled, and classical methods like density functional theory methods don't work well. But this is the bread and butter of quantum computers. So once again, you identify can really use the use of combination of quantum computers and classical techniques help us to do something which we can't do, where experts have problems now. And this is what we are doing also for this specific field.
So maybe I'll ask one more question before we go to the audience. But I think Ingrid had a line earlier about how in mathematics we're building tools, and you don't necessarily know what they're going to be used for, right? And I think we probably feel very similar about quantum computers. They're a tool, and we have some ideas of what we might use them for. But I think what's really exciting is all the things that we don't know that we're going to use them for in the future. But one of the challenges is really figuring out what are good problems and how do we map them onto our quantum algorithms. So I want to see if anyone has thoughts on how do we identify good problems. What's been your experience with that, maybe working with partners or...
So I'm happy to give some insight here. Again, I've been afflicted by theorists who have told me that the only good problems are the problems that are exponentially hard for regular computers. And I guarantee if you're a business leader, you don't care if a particular problem in your supply chain management or your chemical process has a very specific so-called computational complexity scaling. You care about, can you solve it better with one tool or another? Does the GPU give you a better answer than the CPU? Does that lead to business value? And so the way we've approached this with our partners at IBM and elsewhere has been to look at where there is a level of underservice of really high-value problems. And so one of the things that we did was with the Army, where they do logistics optimization. They have to move pallets and material and all this stuff, and it has to arrive in the right order. And it has to arrive after being transferred sometimes in 18-wheeler trucks and sometimes in Humvees. It has to deal with traffic patterns on surface streets. This is not in the battlefield. This is just like in urban environments. And because they're intolerant of things arriving in the wrong order, it becomes actually a very hard problem. It's called a constrained optimization problem, right? If you've ever tried to do designing a transport network or logistics supply chain, these all fall in that category. It doesn't matter if, in principle, a graduate student somewhere could write down a conventional classical algorithm that could, in principle, solve that classically. What matters is, for the last 30 years, the Army has been doing this with pen and paper and now with spreadsheets, because there are no solutions, commercially or research grade, that meet their needs. And so what we identified is that we can work directly with this end user who has some interest in new solutions that may deliver value to them, to explore how quantum computers can give benefit. And what we were able to show is that by implementing optimization algorithms on, in fact, IBM quantum computers in just the right way with our clever hardware level optimization, we were able to come up with solutions that were better than the best classical solutions. Now, this doesn't, I want to be clear, we're not claiming quantum advantage. It wasn't fast, or it was still small scale problems where you can brute force it. It's a test, right? It's a test balloon. But here's an example where I cannot prove to you with pen and paper that this is an exponential potential benefit. I can't, and maybe it isn't. But a GPU cannot be proven to be better than a CPU with computational complexity theory. It just is better for certain problems. And we've clearly embraced that. So we've taken the approach of working with end users who have hard problems, understanding what their constraints are and why they're not getting their solutions available from what has commercially been around, and seeing whether quantum computers can fill that gap. And we've seen actually a huge opportunity there.
Very cool. Yes,
Maybe I'll add a little bit to this, because I do agree that there's a bit of a backlog of problems that we'd love to solve better, faster, cheaper, pick any two. But there is probably even more to be said that comes from the intersection of what this new quantum concept will have with all the other emerging areas that we see occurring right now. And I'll pick on AI for the moment. Quantum's not developing in a vacuum. It's actually happening at the same time as many other novel ideas around computation, physics, and their intersection with each other. So how quantum plays out will depend a lot on how we all intersect and collaborate on these topics. I don't imagine quantum being its own standalone component. I see this convergence happening. Most importantly, what I hope occurs, I'm afflicted as well, but I'm afflicted by the past, which is I have a preset notion of what's possible, and that partly from what I've been exposed to over many years of formal training. There are things now, though, that I believe are possible that I can't yet accept, but I know people not yet afflicted will be able to take that on and pursue those with much more passion and much more clarity than I think our current generation can. So going to your point, I think there is a wealth of things that we've yet to uncover that we'll be able to do with quantum and all these other technologies, simply because it's so new, it breaks so much ground that we're having to overcome our own biases in order to get to that stage.